Hi, everyone. Welcome back. Today's speaker is Maria Apostolaki. Maria is a final year PhD student at ETH Zurich. She's advised by Professor Laurent van Bever. Her research focuses on internet routing attacks and implications for security and performance. She is particularly interested in the impact of the network on blockchain systems. Her most recent work is on the anonymity of cryptocurrencies. She's the first author of 6 different papers, including Securing Internet Applications from Routing Attacks, Saber, Protecting Bitcoin Against Routing Attacks, and Hijacking Bitcoin, Routing Attacks on Cryptocurrencies, which won the 2018 IETF-IRTF Applied Networking Research Prize. And I found out as of today has been cited 280 times. During her studies, she's also worked on buffer management as a visiting student at MIT, and on analyzing data center traffic as a research intern at both Microsoft Research and Google. Before joining ETH, she earned her diploma in electrical and computer engineering at the National Technical University of Athens in Greece. And I say all of this to prop her up because she is currently on the academic job market. So if you are looking for a good candidate, look no further. Maria, I'll let you take it from here.
So thanks a lot, Jonathan, for the kind introduction, and also both of you, Yanis and Jonathan, for the invitation. So I'm really happy to be here to present you our work on routing attacks on cryptocurrencies. Hope we can also find interesting connection with your work. So this is joint work with my advisor, Laurent van Bever, Aviv Zohar, and Jan Martin and Jan Luller. The latter two are master students at ETH. So routing attacks quite often make the news. You will have probably heard about this Russian ISP that hijacked traffic destined to MasterCard, Visa, and other financial services, or this other Canadian ISP that stole $83,000 from a specific mining pool using BGP hijacking. And the fun part is that the price only gets higher. 2 years ago, we had another BGP hijack that resulted in the loss of $150,000 from users of my Ether wallet. And I want to tell you that this is only the tip of the iceberg of routing manipulations. By analyzing 6 months of advertisements, we found that hijacks are in fact much more frequent than one would expect. In the y-axis of this graph, you can see the number of hijacks that we detected in each of the months showed in the x-axis. We found that multiple thousand hijacks occur every month. Of course, not all hijacks are malicious. Most of them are in fact misconfigurations. In any case, though, they are practical and they do affect internet traffic today. The purpose of our work is to shed light on the impact of routing attacks on cryptocurrencies, taking Bitcoin as an example. Intuitively, Bitcoin should be robust against routing attacks, right? After all, it's a highly decentralized network of nodes that are scattered around the globe. They establish random connections, and they're often multi-homed. Or they use additional relay networks to interconnect. Unlike intuition, though, Bitcoin is highly centralized from both the mining and the routing perspective. To give you an intuition of our findings, in the y-axis of this graph, you can see the cumulative percentage of mining power as a function of the number of networks hosting it. Think of a network as AT&T or Swisscom, for example. Clearly, mining power is centralized to very few networks. Notice, for instance, that around 68% of mining power is hosted in only 10 networks. Similarly, if we look at the cumulative percentage of Bitcoin traffic as a function of the number of networks intercepting it, we see that the Bitcoin traffic is again very centralized. For instance, only 3 transit networks intercept 63% of Bitcoin traffic. Due to these characteristics, 3 routing attacks are in fact effective and practical today. First, the partitioning attack, in which the attacker splits the network into 2 disjoint components. Second, the delay attack, in which the attacker delays the block propagation. This is very worrying because it essentially compromises the openness of the protocol and prevents clients from using Bitcoin securely and contributing to the network. And finally, these characteristics allow an attacker to do what we call the perimeter attack, which basically de-anonymizes clients. This is also very worrying because all transactions are in the blockchain, the Bitcoin blockchain, so it's very easy for somebody to infer all the history, all the transaction history. And there are actually surveillance companies that crave for this kind of data. So in this talk, I will focus on the partitioning attack, which is the most effective and general attack. The partitioning attack is an active attack, as the attacker needs to perform a BGP hijack first. This attack is visible, but it's also very effective, even against the Bitcoin network as a whole. The two other attacks are passive, as the attacker acts on traffic's natural intercepts. These attacks are completely invisible, but they're only effective against a targeted set of nodes. So this will be the outline of my talk. I'll first give you some background information. Next, I will describe the first out of the three attacks that I presented before, and I will finish the talk with describing Saber, a relay network we designed in order to defend against the partitioning attacks. Bitcoin, as you know, is a distributed network of nodes that establish random connections. Each node keeps a ledger of all transactions ever done in Bitcoin, which we call the blockchain. And the blockchain is basically a chain of blocks, which is extended by miners. And miners use a lot of computational power for this, and they're compensated by the block rewards. Miners collaborate, forming mining pools, which are often multi-homed. Multi-homed mining pools use multiple regular nodes, such as node E and C in the slide, as gateways in order to connect to the network. Bitcoin connections are routed over the internet, and the internet is composed of smaller networks, which we call autonomous systems, or ASs. BGP is the protocol responsible for computing the forwarding path across them. Bitcoin messages are propagated in the internet unencrypted and without any integrity guarantees. Thus, any AS in the forwarding path can eavesdrop, modify, or delete them. Notice that even if Bitcoin was encrypted, the ASs in the forwarding path would still be able to distinguish and drop such messages. I will now talk about the partitioning attack. The goal of a partitioning attack is to split the Bitcoin network into two disjoint components such that no information can be exchanged between them. The impact of such an attack is really worrying. First, it is an effective denial of service attack, as transactions cannot be propagated. Second, it can cause revenue loss, as all blocks mined within one of the two components will be eventually discarded, together with the pulse rewards. Finally, during a partitioning attack, Bitcoins can be spent twice, allowing for double spending. So let's see how this works. Let's assume that an AS in the middle is malicious and wants to partition the network in the left and the right side using BGP. As an intuition, the attacker will try to attract the traffic destined to all nodes in the right side. To understand how this is done, we will focus on node F, which is the green node in the corner of the slide. I'll now describe how the attacker can attract traffic destined to the green node using BGP hijacking. The green node has an IP that belongs to its provider, namely AS6. AS6 is responsible for informing the internet about the prefix covering this IP. To that end, ASC will create a BGP advertisement that will be propagated AS by AS until all of them learn a path towards this prefix. For instance, AS1 will follow the path via AS7 and AS6 to reach the green node. What is important here is that BGP does not check the validity of advertisements. As such, any AS can advertise any prefix. Let's assume that the attacker also advertises a prefix that covers the IP of the green node, and is also, the attacker's advertisement is more specific, as it's a /24 compared to the /23 of the benign advertisement. Since routers in the internet use longest prefix match, all of them will use the malicious advertisement. This will cause all traffic to the green node to pass via the attacker. This is what we call the BGP hijack, and this is exactly what the attacker will use to intercept all traffic destined to nodes in the right side. She will then drop all the connections bridging the partition, and boom, the partition is created. In practice, creating a partition is not that trivial. There are partitions that can even be invisible to be created, and that is because there are connections that cannot be intercepted. There are three kinds of such connections: connections within a mining pool, connections within an AS, and private connections between mining pools. The main reason why the attacker cannot do that is because she cannot distinguish this type of connections. Even in these cases, though, the attacker can detect that the desired partition isn't feasible and build a similar but feasible one. To give you an intuition of how this can be done, let's assume that the same adversary wants to create a different partition. So this one, the one denoted by the red line. We will also assume the presence of a mining pool in the topology. The attacker will again hijack all nodes in the right side, so the orange nodes in this slide. But now, and she will drop the connection that crossed the partition. And now, as we observe, the partition has been created, but it's not effective. And that is because there is a connection that the attacker failed to cut. In fact, the attacker was unable to cut this connection because it's an internal pull connection. So in fact, the partition was infeasible. However, the attacker can monitor the connection she hijacks and detect the leak of information between the two components. For instance, she can detect that a block mined by the black nodes is advertised by the orange nodes. In fact, she can even identify which node was the first to propagate this information, which is also the node that has the stealth connection. Once she does that, she can remove it from the initial isolated set and create another partition instead. In the paper, we explain the algorithm that the attacker will use to do this and prove that the attacker will always be able to isolate the maximum feasible subset of nodes she initially wanted to isolate. We evaluated our attack in terms of practicality and time efficiency. To evaluate the practicality, we first had to infer the actual Bitcoin topology, which we augmented with routing information. Using this, we found that splitting the mining power even to half, which is the worst case partition for Bitcoin, can be done by hijacking less than 100 prefixes. Looking at it in perspective, a hijack of 100 prefixes is negligible compared to the hijack that happen in the internet regularly. As an illustration, this is a graph that shows the maximum number of prefixes that were hijacked at once in each month. As you see, hijacks involving up to 1,000 prefixes are frequently seen in the internet today. We also evaluated the attack in terms of time efficiency. We first measured the time required to perform the partitioning attack by attacking our own nodes. To do this, we hosted few Bitcoin clients here at ETH, which were connected to the Bitcoin network and whose prefixes we advertised via Amsterdam. As such, all traffic destined to our nodes was routed through Amsterdam. Next, we attacked our own nodes by hijacking their prefixes from a BGP peer that was hosted in Cornell. We then measured the time required for traffic to our nodes to be diverted from the initial route via Amsterdam to the malicious route via Cornell. We summarize our results in these graphs. At the y-axis, we see the cumulative percentage of connections that were intercepted by the attacker as a function of the time this took. We found that it takes less than 2 minutes for the attacker to intercept all the connection. This is the time it will take for the partition to be created. On the other hand, it would take hours for the hijack to be resolved. This is so slow because it's a human-driven process. For instance, note that even Google took 3 hours to resolve the famous Pakistan hijack. So far, I hope I have convinced you that partitions are effective and also practical. In the rest of the talk, I will show you that they can actually be mitigated. I'm sure many of you have already thought of a few countermeasures. For instance, a short-term countermeasure is to host all Bitcoin clients to /24 prefixes. This will reduce the attack surface as the attacker would be forced to compete with a benign advertisement. A more effective but harder to deploy countermeasure would be to use secure routing protocols, which should prevent the BGP hijack altogether. And I hear you. Okay, not literally thanks to COVID, but I understand that these countermeasures are not practical. We cannot host all our clients in /24, and as this will increase our routing tables. And secure routing protocols, yes, they're awesome, but they're not there yet. And they will not be there just because of Bitcoin. There's a clear need for a more practical shield against partitioning attack. With this in mind, we built Saber. Saber is an additional channel that is engineered to allow Bitcoin clients to exchange blocks, even if the Bitcoin network is partitioned. And this is without the need of deploying secure routing protocols, which is significantly harder to enforce. As an illustration, if we were to add Saber in this topology, we would add 3 special Bitcoin clients that will be connected to each other, and each Bitcoin client will be connected to at least one Saber node. As a result, even if the network is partitioned, blocks can still be propagated from one component to the other by the Saber network. Of course, the attacker is expected to fight back by hijacking the prefixes of the Saber nodes themselves or by crafting malicious requests to take them down. Taking this into consideration, we are ready to define the requirements that would allow Saber to meet its promise of protecting the network from partitioning attacks. First, Saber needs to secure relay-to-relay connections because otherwise it cannot relay blocks from one component to the other. Second, Saber needs to remain reachable by Bitcoin clients, otherwise it will be just an independent network. And finally, it needs to remain to relay blocks seamlessly, sustaining any malicious or benign load. The first two are addressed by Saber's network design, while the last one is addressed by Saber's node design. First, I will explain how Saber meets the first of its requirements, namely securing the relay-to-relay connectivity. To do so, Saber selects nodes that satisfy 3 properties. First, all relay nodes are hosted in /24 prefixes. By doing so, disconnecting the relays with longer prefix hijack is not possible because prefixes longer than /24 are not propagated in the internet. So we're left to deal with same prefix hijacking. To understand the problem, let's assume that relays A and B are hosted in ASs that have a customer-provider agreement. Namely, ASA pay ASB for the traffic it sends. Among other prefixes, ASB will advertise the prefix of relay B to ASA. Since there is no other advertisement, the relay A will connect to relay B via the direct and expensive link. Yet, PGP is a policy-based protocol. When multiple same prefix advertisements exist, cost is the decisive factor. As such, if ASA has a more cost-effective agreement with an AS that happens to be the attacker, and the attacker advertises the relay's B prefix, ASA will choose the attacker's advertisement, allowing the attacker to intercept and drop the connection between the 2 relays. To avoid this, Saber places relays in ASs connected with paths that are optimal with respect to cost and distance. As such, there is no attacker that can offer a more preferred path. For example, if ASA and B had a more cost-effective agreement to each other than to any other AS, by definition, it would not have been possible for an attacker to hijack the connection between them. Of course, this can easily change in case the link is cut or an agreement is cancelled. In this case, the attacker's advertisement is the only available, so she can again disconnect the relays. To protect against this, Saber requires the relay graph to be K-connected. Such a Saber network will stay connected even if K-1 links are cut. As an illustration, by adding another relay, the Saber network becomes 2 connected. As such, any single effective hijack cannot cause the relay network to be disconnected. In this example, relays A and B will exchange blocks via relay C, even if the direct connection is hijacked. Our second requirement from Saber was to remain reachable by Bitcoin clients. To do so, Saber positioned nodes such that most clients are protected from each potential attacker by at least 1 relay. I won't talk extensively about this, but I will try to convince you that this works by discussing some of our key results. We evaluated Saber's network design by its effectiveness against 2 attack types, network-wide and node-level attacks. To evaluate Saber on its effectiveness on network-wide attacks, we ask the question, what is the largest partition each single AES can create? As a baseline, consider that in the current network, any single AES in the world can create partitions of up to 90% of the clients. If we deploy the Saber network of only 6 nodes that are 3 connected, then only 3% of the AESs in the world would be able to create partitions of up to 30%. We also evaluate Saber's effectiveness on the latter attack type. The question we're asking here is how many clients are protected against isolation. As a baseline, observe that in the current network, at most 10% of the clients are protected against only 50% of the ASs. If we deployed a Saber network of only 6 nodes that are 5 connected, then almost 90% of the Bitcoin clients will be protected from 92% of the ASs. The last requirement we had from Saber was to relay blocks. To do so, the Saber node needs to maintain connections, receiving, verifying, and transmitting blocks. Saber supports 2 types of deployment. Private deployments, which is designed to serve few predefined clients, and public deployments, which is designed to serve all clients. Private Saber is easy to be deployed, even by a single entity today. That is because private relays only need to establish connection to a predefined set of IPs, while being unreachable by anyone else. And these requirements can be fulfilled by simple software implementation, so nodes can be regular Bitcoin clients that are hosted in VMs in the cloud. On the other hand, a public deployment of Saber is more challenging. In this case, Saber nodes need to be able to timely serve thousands of clients, distinguish spoofing and malicious requests, receive, verify, and relay blocks at high rates. All these requirements cannot be fulfilled by simple software implementations. To deal with this, Saber can leverage programmable data planes. By programmable data planes, I'm referring to network devices that can be programmed to perform various operations on packets at line rate. I will refer to this kind of deployment as SaberDB. There are 3 reasons why SaberDB manages to deal with the high, malicious, or benign load. First, it is faster than any server optimization, able to serve a few billions of packets per second. Second, we have augmented our implementation with protections such as dynamic black and white list, protection against spoofing, and repetitive requests. Third, SaberDB involves minimum software interactions, so almost all clients are served directly from hardware. Of course, not all operations can be done on hardware. For example, the network design cannot validate a block, so the switch itself cannot validate a block. So we use the hybrid software-hardware design. The software part is a regular Bitcoin client responsible for validating new blocks and updating the hardware part as if it were a cache. The hardware part can be implemented in programmable switches, so in the programmable data planes that I was referring before, and is responsible for broadcasting new mine blocks to thousands of peers. To summarize, in this talk, I showed that Bitcoin is vulnerable to routing attacks, that their potential impact on Bitcoin is worrying, and that countermeasures exist, Saber being a good, readily deployable alternative. So if you're interested about this topic, you can find most of the information that I described in the 2 first papers, so in the SP 17 and the NBSS 19. If you're interested in the more broader spectrum of routing attacks and how they affect any service in the internet, then a good source is our paper on the CACM as an article. And finally, there is another attack that is currently under submission that is about the anonymizing clients that I think is an interesting read if you're interested. And with this, I conclude my talk. Thank you so much. I'm happy to take questions now.
Fantastic, thank you. Looking for my little applause icon, but I can't find it. So, okay, folks, feel free to jump in and ask questions. Yeah, Carla, there she goes with the applause. If you don't want to be in the recording, this will be publicly posted. Feel free to drop a question in the chat and I can read it out for you. If you have anything, please feel free to jump in. Yeah, so with that, questions.
Hello, I have a pretty basic question. Do you think the attacks that you have identified are applicable to other networks other than Bitcoin? They seem like they can be applicable pretty much to any blockchain. Is that the case?
So that's a very good question. Indeed, the partitioning attack that I described is definitely an attack that can be applied in any blockchain that uses the internet. So it's a very basic point that any blockchain will need to communicate to reach consensus, and if this is violated, and it can be violated with BGP hijacks, then it cannot work. Now, what differs depending on what you're targeting is the effects on the blockchain. For example, for Bitcoin, it will be super bad because the protocol will continue to operate. So you will still do transactions, you will still mine, you will do everything. There are protocols that mostly appear after our work that would detect that the network is under attack and will pause. In which case, it's still an attack, but it will be a denial of service attack. So you can limit the effects, but definitely it works in other blockchains. Now, for the other two attacks, so for the delay and for the perimeter, um, for Bitcoin, they're particularly effective, and this is because they use the fact that Bitcoin travels unencrypted in the internet. So the delay attack, you would actually change the content of the messages. And by this, you will change what blocks are propagated. So you can actually eclipse nodes very, very easily. This would not work as it is. The perimeter attack would also work. So let me tell you first a little bit what a perimeter attack is, and then I will explain why this is more general. So for Bitcoin is pseudonymous. That means that you can do a transaction using a pseudonym, right? So an attacker cannot trivially map your transaction to your name. However, you will have to do this transaction via node, and the node will have to tell its peers that this is in your transaction such that it gets into the blockchain. Now, if you're in the network, you can observe these messages and the propagation pattern and realize that certain transactions have a special way of being propagated. And that is true even after the improvements of Bitcoin, like diffusion, that tries to make this pattern more random. So with Bitcoin, despite all these improvements, it still works. And one of the main reasons is the fact that it's unencrypted. Now, if we go to blockchains that are encrypted, for example, let's take Ethereum, perimeter would still work, and it would work because the network sees a very important thing about the node it tries to target, and that is the IPs of the nodes it is connected to. And there is previous research on Bitcoin that proves that if you are able to kind of surround the node that you want to target and de-anonymize, you can do it very efficiently. So the point being that being in the network layer, so being an attacker that controls internet infrastructure, gives you a lot of power because it's something that people don't usually take into consideration while they are implementing application level protocols. So yeah, I think they generalize, and yeah, that's the short answer.
This was a really great presentation, Maria. I keep telling folks at PL that we have so much to learn from really great academic speakers, just in terms of the ability to put together a good presentation and move through it. Not that we don't have great speakers, but it's a special skill that folks within academia are able to cultivate, and you did a really great job. Okay, so if you are watching on YouTube, please remember to hit the like and subscribe buttons and share this video. If you want to suggest a topic or a speaker, there are instructions on how to do that in the description, or you can email research@protocol.ai. We'd also love to have you join our mailing list to receive quarterly newsletters, future talk announcements, and information on research funding opportunities. You can do this in the footer at research.protocol.ai. Our next talk is Tuesday, November 17th, that's next week, at 1700 UTC from Dimitris Kolonelos from IMDEA. His talk title is Incrementally Aggregatable Vector Commitments and Applications to Verifiable Decentralized Storage. This will be the last talk we do in 2020. We're going to take December off, but we'll be back on January 12th with a talk from one of Protocol Labs' independent researchers. If you want more details, be sure to sign up for our mailing list. Thanks for joining, everyone. We will see you next time.